So I'm going to be talking about a theory-independent framework for testing gravity on all scales in cosmology, and I'll explain over the next few minutes what I mean by this. So this is based on work I've done with my PhD supervisor, Tim Clifton, and also some work he did with Viraj Sangai. And you can see the papers that this is based on at the bottom of my screen, and I've attached the archive numbers for anyone who's interested or wants to read in more detail. So first off, well, why test gravity in the first place, particularly from a cosmological perspective? Why test gravity, given that we already have an existing theory, general relativity, which is very successful, and indeed associated with it is a lambda CDM model of cosmology that's had a number of successes. However, there are some problems with the GR and with lambda CDM. So in particular, they require dark matter and dark energy in order to account for the things we observe in the universe. And ultimately, a fundamental theory of what those are isn't known. From a more kind of data point of view, we know that there are tensions emerging in cosmological data sets, such as the famous H0 Hubble tension. And this indicates that there might be problems in the lambda CDM model and therefore potentially problems in GR as well. And ultimately, from a theoretical perspective, we know that ultimately gravity will need to be quantum completed, and that indicates that there may need to be some modification at some energy scale. So for these reasons, among others, a lot of people over the years have proposed modified theories of gravity. So theories that have actions different from the Einstein-Hilbert action and therefore introduce different new gravitational effects. However, as you can see from the schematic by Tessa Baker that I've shown on the screen, there's an enormous landscape of modified gravity theories, lots and lots of different ways of modifying GR. And it's very difficult then to obtain a generic statement if, say, one just tests an individual theory and constrains, say, the parameter space of that theory. What we would like to do is constrain large regions of the landscape at once, or potentially even rule out whole regions. And that would be a more powerful and more holistic way of studying gravity. So this is what we try to do, and we do this using our observational tests. And these can sort of broadly be split into two regimes. So we have the small astrophysical scales, where one has tests like tests in the solar system or using gravitational waves, for example. And then we have the large scale cosmological tests. So for example, weak lensing tests, or those to do with the cosmic microwave background, for example. And these are talked about in very, very different ways, typically. So for the small scale astrophysical tests, often people talk about post-Newtonian frameworks, or the parameterized post-Newtonian PPN framework, which we'll talk about more in a moment. And then on large cosmological scales, people talk about cosmological perturbation theory. And these are two very different languages that don't naturally talk to each other in their raw form. So what we would like to do is to be able to construct some kind of dictionary that allows us to combine our constraints that we contain in these two disparate regimes to say something more generic about gravity and about potential deviations from GR. So this is our kind of our broad goal, is that we want to construct some theory-independent framework that can constrain large regions of the landscape and can do that in a consistent way over a wide range of length scales. So all the way from the astrophysical settings to the cosmological ones. And we on a more sort of technical level, we probably want this framework to not be too sensitive to very fine theoretical details. So this is our kind of goal, and what I'll show here is that we've put together a framework that satisfies these criteria, in particular for use in cosmology. So, what do we have to go on for this? Well, we know that such a framework does exist in the astrophysical regime. So this is the PPN framework that was originally built to study astrophysical tests in the 70s. So for example, for things like the bending of light by the sun, or for the Shapiro time delay, for example. And what this does is it says that locally one can describe the space-time metric as equal to the Minkowski metric plus some small perturbation. And then those perturbations are related to, say, the matter content through a small physical set of parameters. So for example, the parameters I've shown in red, So the gamma is the famous light bending parameter, which has been very, very tightly constrained to be very close to the GR value of 1. And then an additional one, gamma C, which we introduce for a sensible cosmological background. But I don't want to get sort of too hung up on the specific details. The point is that we have this framework that very tightly describes gravity in small scales. And then what we're going to do is we're going to build our cosmology out of this. So we're going to build from the bottom up using this framework. And this means that anything we then obtain in cosmological scales will automatically be consistent with our small scale physics. And also, again, a more technical point, I note that this PPN framework makes no restriction on the density contrast. It doesn't need to be small. And this is useful in cosmology because it means that we can extrapolate down to the small scales rather than just being limited to linear scales. However, you can't just take, it probably doesn't surprise you that you can't just take PPN and kind of naively use it in cosmological settings, because it's built on local asymptotically flat space-time, and in particular, it doesn't allow time variation of our parameters, and this is obviously not going to be true in a cosmological context, where, for example, a modified gravity theory might have a varying effect of Newton's constant. And it's also not going to hold over large scales where the Hubble flow velocity can become kind of close to the speed of light, for example, or even exceed it. So we're going to need to go a bit further. So this is what our solution is. So we know that on small scales, so say, somewhere between 10 and 100 megaparsecs, that we expect that our post-Newtonian description is valid within that region. So what we do is we construct many of these and describe gravity in that way in each of these regions. And then we just stitch a load of these regions together using appropriate junction conditions. And if we do this, then we find that the combined kind of global system has an expansion that's described by generalized Riemann equations. And I'll show the form of those equations in a moment. So this is a kind of a schematic of what we do. We start with our small scale post-Newtonian perturbations. We transform from a perturbed Minkowski perspective to perturbed FRW perspective, and then we have our kind of cosmological perturbations, so the kind of familiar phi and psi, and then also a vector B. And then if we can then stitch many of these regions together, we construct a cosmological model. So we obtain these generalized Riemann equations. So for example, if you look at the Hubble squared equation, you have a coupling gamma to the average density, for example. And then we also obtain local equations for the perturbations. So these are just valid on small scales. So for example, we see something like a modified Poisson-like equation, right? So this gamma, now unlike in the classic PPN formalism, because we're considering cosmological timescales, this is a function of time. But it has this form, and that means that we can relate it very closely to our solar system tests, for example. So we're explicitly relating our cosmological gravity to our post-Newtonian gravity. But I said that we want to describe all scales. So we're also going to have to, if we're talking about cosmology, we're also going to have to talk about very large scales. So scales larger than the horizon. So in order to do this, we use an observation originated by Bertschinger, which is that if we have these very, very long wavelength linear perturbations, these are just an equivalent to another FRW universe with kind of perturbed coordinates, for example. And by doing this, you can construct equations for these very long wavelength perturbations. So this is what you see here, and what you can notice that most of this equation is completely theory independent. So the theory of gravity is only going to enter in on the right-hand side through, for example, this H prime term, because this is where, and the point is that this is now a general feature, because we can relate those terms to our PPM parameters, because we have our generalized Riemann equations written in terms of those. So we've also now written our large-scale perturbations in terms of our PPM parameters that we can measure. So if we put it together and we combine our small-scale post-Newtonian analysis with our large-scale kind of separate universe type analysis, and we smoothly join this together, we get our generalized Riemann equations already, but we also have perturbation equations that will be valid on all scales, right down to the highly nonlinear scales and right up to the superhorizon scales. So these equations look like this, and I don't want you to sort of worry too much about the precise form. But the point is that we have now these smoothly joined parameterization functions, such as the mu and nu that I've highlighted there, and also the g and q. And the point is that both on the very small scales and the very large scales, these can be explicitly related to PPM parameters, and that's what I'll show in a moment. So this is what they look like. So these parameterization functions, for example, the mu function that I show in the equation here, we know that on very small scales where k goes to infinity corresponds to small length scales, this just becomes that astrophysical light bending parameter gamma. And then on very large scales, much larger than the horizon, it becomes the combination that you can see. And then similar things hold for the other parameterization functions. So the point is we now have a framework that has equations valid on a very, very large range of length scales, and where across those different regimes, we can smoothly describe them using our observation accessible parameters. So in summary, there's a very large landscape of modified gravity theories that people are interested in testing, and it's useful to construct theory independent frameworks in order to study those potential modifications systematically. And we've developed such a framework that is sort of suited for use in cosmological tests of gravity. So thank you for listening, and please feel free to ask any questions. Thank you.
Fantastic. Thank you again. We've got time for one question, if there are any to come in. Maybe I'll ask one then. So I didn't quite understand how the stitching process helps you get around the problem of things varying on large scales.
Okay.
If you're stitching together identical regions, or are they each independent?
So the point is that these regions are large enough, so say for something like 100 megaparsecs. So let me maybe show the slide again. That might make it a bit easier. Yeah, so these regions are large enough that although they don't have to be identical, but if one averages the density in each individual one, the difference in density between them, so say if they're 100 megaparsecs wide, will be one that we can describe in a perturbation theory fashion. So within each region, they can be sort of arbitrarily inhomogeneous, but then if we stitch them together and make them large enough, then we can use sort of appropriate junction conditions to sort of keep everything well regularized. It's quite, I get that may not be a sort of a totally satisfactory explanation, but I refer you to the original paper by Viraj and Tim, where they sort of go into some detail into how you can do this in a sort of a well regularized way.
Okay, and there's a question from Patrick Sutton. Can you explain a little more about how the mu and nu are fixed?
Okay, yeah, sure. So again, let me go to maybe the final slide. So the point is that these are sort of a smooth function. So they're functions of time, obviously, of cosmic time or conformal time or whatever, and also of spatial scale. And the point is that we don't know what they look like in a sort of intermediate regime precisely. What we do know is that on very small scales, they have to be fixed to be, for example, the mu has to be fixed to be gamma because it has to be consistent with the post-Newtonian framework on the kind of the small scales where that framework is correct. And then on very, very large scales, it has to take a form that correctly relates it essentially to the Friedmann background. Because, for example, if you have, say, H double prime in here, you know that would relate, for example, to time derivatives of your ppm parameters. So the point is that although we don't know the exact form of mu and nu at all points on the kind of the k axis, we know what they would have to look like in certain limits if we can observationally constrain those parameters, say in the solar system, whatever. And therefore, if we smoothly join between them, we can get a handle on how the potentials, say phi and psi, for example, must be behaving across the whole range of length scales.